Raise the roof, roof, roof.
Okay, this is the introduction to work. In class, some of the notes you took, the very first notes, we listed the types of energy. One type is mechanical energy, and I'm going to put a star next to that, because that's going to be the important one for this chapter. Another one was chemical. A third one was electromagnetic. A fourth one was heat. And the fifth one was nuclear. Okay, and those are the ones that we mentioned in class, with mechanical being the most important. Okay. From mechanical, so far, we've mentioned both kinetic energy and potential energy. We'll get to potential energy in the spring, but for now, we're going to focus mainly on the potential energy due to position like gravity. Okay, so how high the object's off the ground will give it more potential energy. All right. Now, the one thing that needs to be noted is that we never lose energy. Okay, I use the phrase sometimes that we quote unquote lose energy. But that's actually not a valid statement, okay? When I use the word lose energy, basically what I'm saying is we are converting from one type of energy to another. So for example, let's say we have a roller coaster and it's going down this hill. Okay. Well, energy is going to be quote unquote lost during that, because really what's going to happen is your mechanical energy due to friction is going to be converted into some heat energy. Okay, thermal energy. All right, now that's going to heat up the bearings. It's going to heat up the track. It's going to heat up the cart. All right. It might be a very small amount, but you would still notice that a little bit of energy is lost, and that the cart is not going as fast as it should be at the bottom of the hill. Okay, so I want to make that statement ahead of time about losing energy. I'm going to probably use the terms, use that phrase, but just realize that all we're doing is converting from one type of energy to another. So for this introduction, we're going to make a relationship between work and energy. Okay, work, by definition, if you look in a physics book, I don't necessarily like the definition. Basically, it's almost like the equation written into words, which I do not like. Okay, the one thing we need to mention about work before I write anything else about the equation is that work is the link between force and energy. Okay. Because really in the end, and I'm going to make a statement here, that work is energy. Okay. So a lot of the problems that we did in class before, where you had to solve for the acceleration, and we needed force, and we used Newton's laws, and F equals ma, and the kinematic equations, we still may use some of that, but really we can just look at the energy in the system to determine how much work was done on the object, and then therefore be able to determine the forces on an object, okay, whether it's friction or just some other force. Right. Okay. The next statement I want to make is the definition of energy. Because like I said, I can write work out as far as the definition goes, but we're going to write the equation, which is the definition. Okay, so energy is the ability to do work. All right, so just read that a couple times. Energy is the ability to do work. So if work's being done, there has to be energy. And if energy is being present or being put into a system, then work is being done on the system. Okay? So really in the end, and this is a statement that some people might not like, but energy is work. okay? Or energy equals work. And that's one thing you're going to have to realize, that we're going to have work equaling energy when we get to these problems. Okay. So let's finally write down the equation for work. A lot of books will use F cosine theta x. All right. Make a little picture here. Let's say I have a flat surface. I have a box on that flat surface. Okay. The box is going to be moved to the right to this position. Okay. The box moved a certain amount of distance, and really in this case, displacement is what we care about. Right. That's our x, displacement. And of course, some force would have had to have been applied to it to get it to move to that position, which is our f. Okay. This cosine theta, I don't really think is totally necessary if you understand how to calculate work. Right? So in the case above here, work is just equal to the force times the change in displacement, or just x, because we assume that we start at x equals 0. In the equation down here at the bottom, I'm going to have the same situation. The box is moved over here, but the force applied to the box, it's my x. The force applied to the box is a little bit different. It's not horizontal anymore like this. It's going to be slightly vertical. And if you remember, we always end up finding components whenever we have an angle involved. So that's my theta. So maybe this is starting to make a little more sense down here. Okay, F cosine theta. So really, F cosine theta is simply Fx. Or, more importantly, it's the force in the direction of motion. Okay, where's this box moving? It's going from here to here. Okay, well, what force do I need? I need a force that points in that direction. Well, that's Fx. Okay, if I apply this equation to the top, what's theta? Well, theta is 0, and cosine of 0 is 1. So it just comes back to this equation right here. So WF change in x in W equals F cosine theta x is the same equation. You just need to be careful about the angle that's involved. Okay. If you don't understand why the top's 0, well, the force is in the same direction as the motion, so there's no angle involved. Right. So that's when we have work done. Work is done when there's a force and there's a movement of an object. Okay. Now there's two situations we're going to say when no work's being done. I guess we could say 3, but the first one, if the box doesn't move at all ever, of course no work's being done, and I think that's kind of obvious. Right? The first situation where we have work equaling 0, right, is basically, let's say flat surface, box starts here, you move the box over here somewhere, and then you move the box back to where it started. So what's my x value then? If I started and stopped in the same spot, well, it's equal to 0. Okay. Well, if I do the equation, W equals F change in x, with this equaling 0, my W is going to be equal to 0. Okay, so that's one situation. The second situation is when the force is applied perpendicular to the object. So let's say the motion of an object is to the right, but somehow my force is applied vertically. Well, my angle here is 90 degrees. Okay? If I'd use my equation, F cosine theta x, or change in x, okay, you might have a change in x. That's fine. But the work would also be based off the angle, which is 90 degrees. And cosine of 90 degrees is 0. Okay, so those are two situations where no work's involved. And that's a typical test question I ask. What are two situations? Everybody can normally give me the first one. It's the second one where people get hung up. All right, last thing I want to do with this equation is take a look at the units. We're going to deal with the SI units as usual. Okay. W equals F, change in x. We know that if you have the put cosine in there, cosine of an angle is no unit. Right? So work is actually measured in joules. Okay? And energy is measured in joules. The force is in newtons. And the change in x is in meters. Okay. So really, J for a joule is equal to a newton times a meter, or what we call a newton meter. Right. If you want to break that down a little bit more, which is at this point unnecessary, but you can do it if you'd like, a newton is a kilogram meter per second squared times a meter. Okay. If we want to make it look a little bit better, that would be a meter squared divided by a second squared. Kilogram meter squared per second squared. And this is going to be noticed again when it comes to kinetic and potential energy. Okay? So in this intro, we looked at the major types of energy, okay, the types of energy. We went through two situations where the work is actually 0. We went through the work equations when you would have work being done. I mentioned that energy is work and work is energy, even though some people might not like that kind of statement, but they both have the same units. And lastly, we went through the SI unit. So the SI unit for work and energy is both a joule.